calculus applies to the medical field. Here's my patient.
Oh, God.
He fell off a cow and now is injured.
My uvula.
So first we're going to test his IV, and it's decreasing and going into his bloodstream at a rate of 125 milliliters or cc's per hour. Now we're going to calculate how fast the height is decreasing. Since the radius is constant, we can plug it in as pi 6 squared times height. So then dV dt is 36 pi times dH dt. We already know that dV dt is equal to 125 centimeters squared per hour. So the final answer is 10.908 centimeters per hour. Here's a bolt where cerebrospinal fluid is leaking from his brain. If you can
Ooh, my
follow
brain.
this chart, we're going to find out how much fluid has leaked based on his rate. This graph tracks the rate of cerebrospinal fluid leaking in millimeters per minute over a time period of 14 minutes. In order to find out how much cerebrospinal fluid has leaked over these 14 minutes, I'm going to find the area under the graph. To find the area under the graph, I'll be using the trapezoidal sum. The area of a trapezoid is found by averaging the bases and multiplying by the height. In this situation, the height is the difference between the x values and the y values are the bases. For example, in this first trapezoid, the height is 1 and the bases are 10 and 11. So you would multiply 1 by 10 plus 11 divided by 2 and get the first area as 21 divided by 2. I found the rest of the trapezoid's areas the same way, and when I added them all together, I got 98.75 milliliters, which is the amount of cerebrospinal fluid that left the brain in 14 minutes. The patient's taking morphine to deal with the pain. Here's an equation that represents the amount of the drug in the bloodstream at a time.
I'm dying.
We're going to find the rate at which it is entering the bloodstream. To find the rate at which the drug is entering the bloodstream, I would find the derivative of D. Since this is a fraction, I would use the quotient rule. This is the equation for quotient rule. I set 5t as f and 0.01t squared plus 3.3 as g. F prime is 5 and g prime is 0.02t. Once I plug in all the variables, I get this equation. If I want to find the rate at which the drugs are entering the bloodstream at time t equals 10 minutes, I would plug in 10 for all the t variables. My final answer is 0.622 micrograms per milliliter per minute at time equals 10 minutes. We're going to find cardiac output with the amount of dye injected into the heart and the amount of dye left over time. One way to find cardiac output is the dye dilution method. The formula for cardiac output is Q, the amount of dye injected over the integral from 0 to t of C of t dt, where C of t is the amount of dye remaining at t in milligrams per liter and is equal to 2t e to the 5t squared on the time interval 0 to 10. The amount of dye injected in this situation is 10 milligrams. I'm starting with the bottom denominator of this equation, and I'm integrating from 0 to 10 seconds. So to start, I'm going to set 5t squared equal to u, so that du is equal to 10t. I took the 2 out of the integral, so now all I need to multiply by is 10 to get du. But when I add this 10, I also have to multiply by 1/10 so that the equation remains the same. E to the u stays the same when I integrate, so it's just going to be e to the 5t squared times the 1/5 that came from the outside. This is a definite integral, so I plugged in 0 and 10 for t. Now that we have the denominator of the problem, we can plug in the rest of the information that we have. The answer ends up being 500 divided by e to the 300ths minus 1 liters per second.
3.
Thanks for watching.